If you were one of the kids in middle school who was wondering why is the slope of a line m, and you have most likely been exposed to this fact in middle school that the slope is going to be the constant in front of the x, which is m. But now comes the time to prove it. Now comes the time to prove that the slope is actually m, using our knowledge of derivatives as connotations of slopes. But in order to solve this hard problem here, we're going to need to learn a couple of skills and properties of derivatives. So, namely, what am I talking about? The first property of derivatives we want to prove is that the derivative of a function that is the sum of two functions, f of x plus g of x, is going to equal the sum of its derivatives. So this is equal to d dx, so d over dx of f of x plus d over dx of g of x. Okay? Now, this will also work with the minus, so it should be difference as well. So I encourage you to prove that case on your own after watching this video. So let's get into it. We want to prove that this is true. We want to show. So WTS wants to show. All right, let's start with the proof. The definition of a derivative, recall, I'm going to copy it over here, as a function is defined to be the limit as some change in x, h, goes to 0, of that function with that change in x inputted, minus the original function value of x over h. So let's apply that here. Now in this case, this function can be looked at as h of x, which is a sum of two functions, f of x and g of x. So then in this case, this is equal to the limit as h goes to 0, the actual little difference goes to 0. Some textbooks will use delta x, but I don't really like to use that. It's harder to write than h. So you have f of x plus h plus g of x plus h, all right, minus the original function, which is just f of x plus g of x, and distributing that negative, we get minus f of x minus g of x. And that all goes over h. Now, we're going to rearrange some terms. So what we're going to do is we're going to swap this term with the f of x, just so we can consolidate our colors together. And what this means is we can essentially split this into two fractions, right? Over h over h. And by using our arithmetic of limits, this is the same thing as taking this limit and using it as a linear operator, meaning that it applies to all the terms, independently or together. So this is the same thing as saying the limit as h goes to 0 of f of x plus h minus f of x over h, plus the limit as h goes to 0 of g of x plus h minus g of x over h. And notice that by the definition of a derivative, this is the derivative of f of x, and this is the derivative of g of x. So we can say in the final grand finale, d dx f of x over here, and we add that to d dx g of x. And there you go. You have just proved what's called the linearity of derivatives. The fact that the derivative of a sum is the sum of the derivatives, also written compactly as the derivative as a big D of the sum is equal to the sum of the derivatives. So put down a QED, you've deserved it, you've just proven this, and again, prove the difference rule on your own. Okay, now one more thing, or a couple more things I want to prove, is the derivative of a function times a constant. So what do I mean? The derivative with respect to x of some function c f of x is equal to, right, c, that constant, times the derivative. So like with limits, and the fact that the derivative is defined as a limit should tell you right away that this property is true. Same with linearity too, by the way. So what does this mean? That means we can just hop the c out of the derivative when we're dealing with harder functions. So think of this function again as some sort of function g of x. All right? So this is what we want to show. All right, so we're starting with the left-hand side. We see that that's defined to be the limit as h goes to 0 of some function g of x plus h, which here becomes c times f of x plus h, right? We subtract from that the original, which is going to be cf of x, and we take it over h. And watch this. You can factor the c out of here. So, oh, I got rid of the f there as well. There you go. So c can be factored out of the expression. And then by the arithmetic of limits, we can hop that c out in front. Oh, we just jump back. Here we go. And that means that by the definition of a derivative, this entire expression is the derivative of f with respect to x. So we can say that this is equal to, by definition over here, the derivative with respect to x of the function f of x with just a constant c in front of the derivative. And there you go, you've just proven it. So QED, pat on the back. All right, and the one more thing that I wanted to show, well, actually, again, I lied again. There's two more things I want to show. The derivative with respect to x of a constant function, c, is equal to 0. Now, what's the intuition behind this? Well, let's take a look. Here's our graph, and here's our constant function, c. The fact that we want to know derivatives as slopes shows that this slope here of this line is 0, so the derivative should be 0. But let's prove it. So again, this is defined to be the limit as h goes to 0 of f of x plus h, which is just c, minus c over h. Remember that any value of x will give you the same constant c in the y. So we can write this. Now, c minus c is just the difference of two exact values, which is equal to 0. But now, if you try and plug in h as 0, you get 0 over 0, which doesn't make sense. But here's the key. When we take the limit as h goes to 0, if the top numerator is strictly 0, and we know that it doesn't depend on h, then that means that when we talk about limits, we don't care exactly what h is equal to at 0. We care about what it's near 0. So if we plug in smaller and smaller values of h in the denominator, the numerator of 0 will still keep that value as 0, which means we can say that this is 0, and we can say we've proven the statement, QED. All right? Now I'm going to prove the last statement I wanted to prove. And that's to say that the derivative of the linear function, simply just x, is equal to 1. Now, if you've already looked at derivatives as slopes, you know that if it's mx plus b, this is just the same thing as y equals 1 times x plus 0. So the slope m should be 1. But again, we're not going to be able to use this reasoning right now because we want to prove that m is a slope. So, let's take a look. Again, this is defined, so again, want to show. This is defined to be the limit as h goes to 0 of f of x plus h, which in this case is just x plus h since it's a linear function, minus the original function x taken over h. And now look, you can cancel out the x and negative x, and look, the h is also canceled to become 1. And of course, the limit of a constant is just a constant, so it's equal to 1. And there you go. So we've just proven that the derivative of the linear function x is equal to 1. All right. Now we're going to address the task at hand of showing that the derivative of the linear function y equals mx plus b is equal to m. All right? Or we would just want to find that that's true. So I'm going to quickly reproduce this below. And using everything we've already learned in this video so far, we're going to prove that. So what we're going to do is we're going to state d dx, right, of mx plus b. Now, what do? Well, we prove the linearity of derivatives, so the derivative of the sum is equal to the sum of the derivatives. So we can split this into d dx mx, like this, right, plus d dx of b. Now we can use a couple steps here, because we know that we've already proved that the derivative of a constant is 0, so this entire term goes to 0. And we also showed that we can just hop the constant, which is m, out of the function. But look, we also proved that the derivative with respect to x of x is 1. So this becomes 1. And we get 1 times m plus 0, which of course is m. And so there you go. We've officially proved that using the idea of derivatives as slopes, that the slope of the function y equals mx plus b is m, so you get dy dx is equal to the constant m. And this is true for any linear function, as you can see. So 2x plus 1 is simply going to be 2, because that 1 goes to 0 and that x goes to 1. So there you go. So then, with this idea of slopes and what we learned in middle school of m being the change in y over change in x, you can see the similarities between the derivative of dy dx and delta y delta x. Delta y connotes a finite difference of values, so some value y2 minus y1 over some x2 minus x1 for 2 points, right? And that describes the secant line. So you can think of dy as delta y going to 0 and dx as the change in x going to 0. And that's clear with the idea of secants turning into tangents as this line gets closer and closer, and as this point on the curve gets closer and closer to the original point. That line becomes the tangent. So I hope that this entire video has helped you understand how to prove some of those very important properties of derivatives and how we can actually prove that age-old question of what is the slope of the linear function. Till next time.